Let's talk about the Wronskian. First, a review of the definition of linear independence. A set of functions f1 of x, f2 of x, blah, 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 fn of x is linearly independent on an interval if the only values of the constants c1, c2, blah, 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 cn, which make c1 f1 of x plus c2 f2 of x plus blah, 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 plus cn fn of x equals 0 for every x in the interval, are c1 equals 0, c2 equals 0, cn equals 0. In other words, of course, if all of these, c1 through cn, if they're all 0, then obviously the left side is going to be 0 as well. The question is, are there other values of c1, c2, etc. that are not all 0 such that we can make the left side 0? If the only values of c1, c2, blah, 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 which make this left side 0, are c1 equals 0, c2 equals 0, etc., then we say the set is linearly independent. But if there are values of c1, c2 that aren't all 0, that make that left side equal to 0, we say the set is linearly dependent. Let f1 of x, f2 of x, blah, 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 fn of x be a set of n solutions of a homogeneous linear nth order differential equation on an interval. The set of solutions is linearly independent. So again, this is another way to determine if it's linearly independent besides the definition. So that set of solutions is linearly independent if and only if the Wronskian, named after the great Polish mathematician Joseph Wronski, in Polish we'd say Józef Wronski. So this set of solutions is linearly independent if and only if the Wronskian, w of f1 of x, f2 of x, f sub n of x, which is equal to this determinant, is non-zero everywhere in the interval. So again, notice this determinant. The top row is f1, f2, all the way up to f sub n. The second row is f1 prime, f2 prime, etc., all the way up to fn prime. And the bottom row is the n minus first derivative of f1, n minus first derivative of f2, etc. So that set of solutions is linearly independent if and only if the Wronskian is non-zero everywhere in the interval. A set of n linearly independent solutions to an nth order differential equation is called a fundamental set of solutions to the differential equation. For example, the differential equation y double prime minus 8y prime plus 12y equals 0 has e to the 6x, e to the 2x as solutions. Determine whether the set of functions f1 of x equals e to the 6x, f2 of x equals e to the 2x is linearly independent on the interval from negative infinity to infinity. We're going to use the Wronskian. So we calculate the Wronskian of this set. The top row is just that set of functions, e to the 6x, e to the 2x. The second row consists of the first derivative, 6e to the 6x, 2e to the 2x. Let's calculate the Wronskian. It's just the determinant, so it's going to be these two, the product of these two minus the product of these two. So it's e to the 6x, 2e to the 2x, minus 6e to the 6x, e to the 2x. In other words, it's going to be 2e to the 8x minus 6e to the 8x, which is negative 4e to the 8x, which is never 0 on the interval from negative infinity to infinity. Thus, the set of solutions is linearly independent. Is the set e to the 6x, e to the 2x a fundamental set of solutions to the differential equation? Let's review what we mean by a fundamental set. A set of n linearly independent solutions to an nth order differential equation is called a fundamental set of solutions to the differential equation. So here, this differential equation is second order, and this is a linearly independent set of two solutions. So in this case, n equals 2. So it is indeed a fundamental set of solutions. That means all solutions will be a linear combination of the two solutions, e to the 6x and e to the 2x. That is, any solution will be of the form y equals c1 e to the 6x plus c2 e to the 2x.